Hi, everyone. My name is Paul. I'm a PhD student in the machine learning department at Carnegie Mellon. And I'm really excited to be here today to share some of my recent research on building towards real-world social intelligence in AI. AI has made significant progress in physical intelligence, the ability to understand and manipulate real-world objects, as well as digital intelligence, the ability to comprehend unstructured data on digital mediums such as the internet. In my opinion, the next milestone for AI will be understanding social intelligence, a trait natural to humans, but still a grand challenge to current machines. My research therefore builds towards socially intelligent AI that can comprehend human social cues, intents, and affective states, engage in social conversation, and understand social norms and common sense, all in order to maintain a rich level of interactions with humans. Building social AI will have major applications in understanding multimedia content, such as online videos, building intelligent personal assistants that can engage people through different social interactions, and eventually pervasive interactive robots that can monitor human behavior to understand the types of help people need and offer their assistance in schools, hospitals, and the workplace. Underlying these desirable applications of social intelligence are fundamental algorithms for multimodal perception and multimodal interaction. On the perception side, understanding social behaviors involves understanding human communication, which is a structured system of social signals used by us to convey our intentions through both verbal and nonverbal channels. Perceiving human communication from a speaker therefore involves understanding these social cues, intents, and affective states, underlying personalities, and references to some broader environment. In addition to perception, interactive social intelligence involves modeling the long-term interactive loop between social perception and action. After a step of perceiving human communication, social AI agents should be able to communicate through multimodal behaviors and take responsive actions in some embodied environment. In order to enable multimodal perception and interaction, there must be underlying foundations in multimodal machine learning, which spans the fusion of multimodal data, representing multiple heterogeneous sources, aligning one modality with another, translating from one modality to the other, and co-learning from multimodal data. While prior research towards social intelligence has indeed made impressive strides in effective computing and dialogue systems, it is also important to bridge the gap towards real-world deployment in important human-centric areas such as healthcare and education. Therefore, a lot of my research has involved ensuring the accessibility of such models so that no social group will be at a disadvantage when these models are deployed, especially those from underrepresented groups. Therefore, some of my work has focused on robustness, ensuring the robustness to often noisy and imperfect real-world multimodal data, fairness, because real-world data often contains undesirable stereotypical associations that can propagate negative generalizations about certain social groups, privacy, because real-world human-centric data often contains certain private, personal, and protected attributes, and is therefore important to ensure privacy in these large-scale settings. Generalizability, because often real-world data often includes low-resource speech, languages, and images, and therefore is important to ensure accessibility to different demographics. And finally, getting these methods to work in real-world applications, such as healthcare and education. So this slide basically covers a large overview of my research so far. And this talk will primarily focus on some of my recent work covering the real-world aspect. So building better benchmarks to really test for these real-world aspects of multimodal learning, and also some recent research on improving the robustness and fairness of these real-world models. So benchmarks are often the first crucial steps in building machine learning pipelines. So to begin with, some of my research have focused on building reliable, large-scale benchmarks for several core multimodal problems in social intelligence, among one of which is affective recognition, which studies the perception of human affective states such as emotions, sentiment, and personalities from a natural display of multimodal signals spanning language, through our spoken words, visual through different facial expressions and gestures, and audio through prosody and our tone of voice. So we have built some very large-scale benchmarks that contain diversity in speakers, topics, annotations. They all involve a single human speaker expressing their intentions and their behavior and their feelings through these multimodal videos. Having diversity in speakers, topics, and annotations enables us to have generalizable studies of multimodal communications in humans and build large-scale models that learn from data. Recently, we have really expanded some of the benchmarks that we have built by creating a standardized benchmark called Multibench. So Multibench contains a diverse set of 15 datasets that span 10 modalities and test for more than 20 prediction tasks across 6 distinct research areas. So these 6 research areas involve affective computing, as we just discussed. It also includes other domains such as healthcare, robotics, finance, human-computer interaction, and multimedia. We made it a point to include multiple research areas that are each really important towards the pursuit of social intelligence, and also multiple data sets and multiple tasks in each of these areas, because it then enables standardized, reliable, and reproducible large-scale benchmarking of multimodal models. In addition to the diversity in data and domains, Multibench is also designed to really reflect some of these real-world requirements because it holistically evaluates for performance across domains and modalities, complexity during training and inference, and also robustness to noisy and missing modalities. Using Multibench, we've actually uncovered several major limitations of current multimodal models. So firstly, what we have plotted here is the relative performance of each model across in-domain datasets, which we plot in red, and out-of-domain datasets, which we plot in blue. So in-domain refers to the performance of models on datasets that the method was previously proposed for, and out-of-domain shows the performance on the remaining datasets by taking that same model and applying it on datasets that it has not been proposed for. So we find that perhaps unsurprisingly, many of these methods show the strongest performance on in-domain datasets, which these methods were originally proposed for, and the performance drops very, very quickly when they're tested on datasets from different domains, modalities, and tasks. In general, we also observe very high variance in the performance of these multimodal methods across all the datasets in Multibench, which suggests that current multimodal methods are often only work on the small subset of data sets that they were proposed for, and do not work on a larger suite of data sets across different domains and modalities. This therefore suggests open questions in building towards more generalizable models. Another big trade-off we found was that between performance and complexity. So over here, we have plotted on both axes training speed, where faster is better, and performance, where higher is better. So we've plotted a dotted blue line of best quadratic fit to show this Pareto frontier, and show that there still remain strong trade-offs where better performing models usually takes slower to train, while faster models are usually not as good performing. So these strong trade-offs should encourage future work in more lightweight multimodal methods that are still generalizable across data sets across Multibench. The last strong trade-off they wanted to highlight through Multibench is that between performance and robustness. So over here, we have shown two curves, one for relative robustness and one for effective robustness. We find that on the left, better performing methods tend to show better relative robustness, which implies that models that start off with higher accuracy tend to stay above other models on the performance imperfection curve. In other words, they tend to retain higher accuracy. However, in the second plot based on effective robustness, we observe a negative best fit between performance and effective robustness, where effective robustness is calculated by the rate of drops as more imperfections are introduced. Therefore, these are well-performing methods. They tend to drop off faster after equalizing for initial accuracy on clean data. And we've also found that very few models currently achieve both relative and effective robustness, which suggests some major directions for future research. Therefore, the main takeaways are that we hope that this standardized benchmark, which tests for three things, generalization across multiple data sets and modalities, complexity across both training and inference, and robustness between both relative robustness and effective robustness. So I hope that some of these insights can present directions for future work towards more real-world multimodal learning that focuses not just on performance within a single data set and single domain, but rather performance across multiple domains, as well as complexity and robustness. These are all important areas that have to be solved before these multimodal methods can be accurately and reliably deployed in the real world. So using some of these insights and some of these data sets within multi-bench, some of our work has also focused on solving some of these issues. So building towards methods that are more robust in the face of noisy and imperfect multimodal data. So in one of our works, we have used tensors to represent multimodal interactions. Tensors are a very good abstraction for multimodal data, and they are suitably expressive because they allow you to capture multimodal, to capture all the interactions between different modalities. At the same time, we actually have this insight that noisier data, so the presence of a Gaussian noise or other various types of noise, as well as the presence of other types of imperfections, these imperfect data often breaks the correlations across time, if you're working with time series data, and also breaks the correlations between dimensions across modalities. And this leads to tensors of higher rank. Therefore, we had insight to restrict the rank of these tensors to ensure the smoothness of these tensor representations over modalities and time. And what we've shown over here is that indeed, clean data shows a low rank, and more imperfect data through either random dropping of your data or more structured dropping of your data leads to tensors of higher rank. And regularizing the rank leads to higher performance across all noise levels. In other words, the curve being higher up over the other curves that do not have this regularization on your tensor rank. So this was both a very simple and effective way, and yet also mathematically motivated method to improve the robustness of noisy and imperfect modalities through tensors. We've also built several generative models of multimodal learning. In this case, we basically assume that the multimodal representation is actually factorized into multiple individual factors. So this enables us to learn representations where each factor models just one variation of the data. So in this case, the factors were your Z's, where there was one factor for each modality that were modality-specific factors that only model variation in one modality. So for example, ZA1 might only model variations in a language modality, so how a person says their words. ZA2 might be a variation in the visual modality, so variations in that person's gestures. And ZA3 might be a variation in the audio modality, so how that person displays changes in their tone of voice. At the same time, we also had a joint factor, so that is denoted as ZY over here, where ZY is a joint factor that represents, in general, how that person varies in terms of the display of sentiment. So that is a joint multimodal factor because the display of sentiment is a multimodal information from language, vision, and audio. We found that these factorized representations were more robust than entangled representations, where everything was encoded into a single representation. And at the same time, having a generative model paradigm allows us better interpretation and also inference of noisy and missing modalities. One last method that we've also done in the direction of robust multimodal learning is this new paradigm of learning multimodal representations through translation instead of fusion. So the classic way of learning multimodal representations takes both modalities, for example, language and vision, both as input into a model that learns a multimodal representation. Over here, our insight is that by translating from language to vision, the intermediate representation learned through translation is actually also a joint representation that can be used for prediction of your multimodal tasks, such as sentiment. But the main benefit of this is that when training, you're trying to learn a translation from language to vision, as well as to predict the label. But during testing, all you need is the language modality that infers this joint representation and then to the label, which means that only language modality is required at test time. and therefore the model is completely robust to any noise or imperfections in the visual modality during testing. We found that these approaches perform as well and even better as methods that take in both language and visual modality as input. But at the same time, because they only use language as input during testing, they're completely robust to any noise and imperfections in the visual modality. So in addition to robustness, another big pillar of my research towards a real-world social intelligence is that of fairness, and particularly under fairness to that of mitigating social biases that might be captured in imperfect data sets. So this is a very important direction because often when we collect data, especially historical data, and especially from human-centric data, there's a risk of exposure bias due to imbalanced data sets. So models trained on this bias data have been shown to amplify the underlying social biases, especially when they correlate with prediction targets. And that has resulted in certain word embeddings, for example, of different gendered nouns being closer to certain occupations as compared to others based on stereotypes from historical data. Some of my recent work has proposed new methods to mitigate the bias in a geometry of pre-trained sentence encoders, such as BERT. And this is super important because while there's been research in mitigating bias in word embeddings, nowadays there has been a fundamental shift towards using these pre-trained sentence encoders, such as BERT, Elmo, and GPT, in order to learn sentence representations that are then useful for a variety of downstream tasks. Therefore, being able to mitigate bias in a geometry of these pre-trained sentence encoders is important so that these large pre-trained models encode less of these social biases when they're used for inference. A main benefit of our approach is that all it needs is a pre-trained BERT representation, and you no longer need to retrain BERT and these other large-scale language models, which is very effective because then you can do multiple debiasing as a post-processing step instead of having to retrain the model from scratch each time, which is usually very expensive. An extension of these pre-trained sentence encoders, which are more used from a discriminative perspective, so used for tasks like question answering and sentiment prediction, we have also recently explored ways of measuring and mitigating these social biases from a generative perspective. So in other words, the generation of sentences using large pre-trained language models. Again, these large pre-trained models are known to be quite dangerous in generating hateful content, especially when these underrepresented groups are used as input. And we have developed some ways of controlling this bias and mitigating these bias in these language models to make sure that they are more reliable and do not generate more harmful content. Again, some of these methods can just be used as post-processing methods in a sense that you can take any pre-trained language model, which takes a very long time to train, but you can just add some post-processing steps that are much more effective. So you can do this multiple times using different sources of bias that might be uncovered in the future. So to finish my talk, I would also like to share a very nice ongoing collaboration with several hospitals and medical schools at the University of Oregon, Columbia University, and the University of Pittsburgh on using multimodal models towards our real-world mental health assessment. This is an important problem because mental illnesses can often have a very damaging permanent impact on communities, societies, and economies all over the world, especially in adolescence, where they're often late in seeking professional help. So intensive monitoring of behaviors by adolescents' natural use of smartphones can actually help to identify real-time predictors of mood as a proxy for suicide risk. So to do so, we partner with these hospitals to analyze a recent data set of mobile behaviors conducted from adolescent populations at different risks of suicide. So this unique data set actually presents us an opportunity to investigate a different medium of NLP using typed text, so text plus the typing patterns, which presents new challenges beyond usually conventionally studied written and spoken text. So we propose several multimodal models to process typed text for mood prediction. However, these models often capture private user identities in their intermediate representations when predicting mood. So over here, you see that using raw features, you can actually predict the the user identity with almost more than 90% accuracy. And if you use a trained model that was just trained using supervised learning to predict the user identity, you can still predict user identity with more than 80% accuracy. On the other hand, the model we proposed that was privacy preserving are only able to predict user identity with about 40% accuracy. So we've also plotted some of these trade-offs in this graph over here, where on one axis we're showing privacy, so privacy based on how well you can predict the user identity, and the other axis we're showing performance, so how well you're able to predict daily mood. And we actually find that these multimodal models that are also privacy preserving are able to increase performance while remaining private, thereby pushing forward the Pareto frontier. So I hope I've motivated why it's important to study social intelligence, and more importantly, several shortcomings of current machine learning and multimodal models that make them as of yet unsuitable for complete real-world deployment. But I've planned to push forward some of these directions in the future, especially on the real-world direction, and hope that some of you watching this will be interested in these directions as well. And all of this work could not have been done without a fantastic group of collaborators in both the academia and industry. I'd like to thank them for all of these collaborations in this paper. And finally, all of the resources that I've talked about are available on my GitHub website, and that includes code and data and benchmarks for all of the works that I've talked about in this presentation. And definitely feel free to ask any questions here at this talk, or also ping me on my email or Twitter if you have any other follow-up questions in the future. Thank you.